So, section 10.1 is temperature and what's called thermal equilibrium. Okay, you've heard the term equilibrium already. Agreed? When did you hear equilibrium?
Diffusion.
Okay, diffusion is equilibrium. That's good. Can we open a window in the back?
No, it's freezing.
Oh, then don't. That's fine. I didn't know you guys were cold today.
Don't tell us what to do.
All right. So, when did you hear equilibrium? For real?
Homeostasis.
Okay, homeostasis, osmosis, those things, sure. Thank you. In physics, we need your free body diagram. We look at force equilibrium. Those are good applications, though, too. All right. So, if you hear thermal equilibrium, what do you think of? What kind of a balance? Instead of force balance, temperature balance. Temperature balance. So, right now, I closed the door. So, this is a closed system. There's no air coming in, there's no air getting out. Granted, the vents obviously have ventilation because we need oxygen to survive, but the temperature is approximately staying at a fixed temperature now, right? It's not going to change much. If we open the window, though, what would happen? Air rushes in, it's cold air mixes, there's convection currents, and eventually it comes to thermal equilibrium once we close the window again, but it's a colder temperature. So when you think of thermal equilibrium, we're thinking about two temperatures meeting somewhere in the middle. Okay? Let's see. The other thing we're going to look at are temperature scales. Okay? Relax. So, temperature, which you've seen this definition before in chemistry. Average kinetic energy of the molecules. Okay? Because temperature is the motion of the molecules. If you take... Remember we tried that can thing and it didn't work? It was ultimate fail? The can, I tried it, it was ultimate fail? Yeah. So, if you take a can or something with a liquid or gas in it, and you heat it up, what will happen is, the gas molecules will start to move faster and faster, which increases the temperature. So as molecules move faster, you have an increase in overall temperature. So if you could somehow add energy to the system, what do you think would happen? If you could add energy to the system, what would you say happens in general for temperature? It rises, right? And a quick little image here. So all we're saying here is this. The molecules are moving slowly. You add energy, cause them to speed up in a closed system. Okay? If you guys don't stop, I'm going to ask you both to turn your iPads down. Okay? All right. So stop. Now, you add energy to the system, it increases temperature, and vice versa, right? So you remove energy from the system, and suddenly the temperature decreases. So if you want to think about how you heat up water, you're putting a flame below the water, which is adding energy to it. Water has a specific heat capacity, and as a result, it increases in temperature. And we're going to see in sections 10.2 and 10.4, or maybe 10.3, I forget, how that works with calorimetry. Remember Q equals MC delta T from chemistry? We're going to look at phase changes in terms of physics and what happens to the molecules.
Two things. One, doesn't add energy to the pot or the thing that you're heating up, and then that.
The burner adds energy to the pan or pot or whatever it is, which then sends the energy into the water via conduction.
And also, did Mr. Joseph ever tell you about his friend who's a rapper and called himself MC Delta T?
Did he really?
Yeah, that's how we remember that equation.
That's hysterical.
Ask him about it.
Why MC delta T though? Because he's...
MC,
So like
like
MC, like
I rap.
Like
Delta T.
Oh, I thought because it had to do... Because it was Q. Like, what does Q mean in rap world? MC delta T?
Someone who's MC.
An MC though is somebody, not a rapper, it's somebody who presides over like a show. Really?
Mark's rapper.
And I know MC Hammer.
What's Mark's rapper? MC. What is it? Just MC.
It's just MC.
It's just MC.
Mark who?
A Kimmon.
Oh, I didn't know he rapped.
No, the other Mark.
He has.
I didn't know. I thought there was a joke to me at first. Like, my name is Mark. Is she like kidding me? I didn't know what that meant.
On SoundCloud.
All right. All right. So temperature as a relative term. Now, I want you to think about this for a second, and there's another opportunity for a little more extra credit.
Oh, we gotta do that.
Okay? One person already did extra credit. Well done.
Did you like
Is
it?
it due Monday?
Monday, the egg drop, or egg squeeze. Egg squeeze. Guess that's a good word for it. A little awkward. So your egg drop is also due on Monday, don't forget.
Take a video of us squeezing it.
What's that?
We should take a video of ourselves squeezing it.
Yeah. When you bring your egg drop experiment in, I'm going to put it in the closets and they're going to be locked, so you don't have to worry. We're not going to do it for a few days, but they are due on Monday. Okay, here's what you do. Ready? If you want to write this down, this is your extra credit thing. I'm not going to explain it. I'll just put it online. I'll put the due date for it. I want you to do the following. Take a bowl of water, relatively big so your hand can fit in it. Okay? Make it warm water, not hot, but warm enough that it feels warm on your hand. Take another bowl on the right side and make an ice bath. So ice water. Fill it with half ice and then fill the rest with water. So it's ice water and warm water. Okay? Put one hand in each. Now, clearly one's cold, one's hot. Agreed?
Wait, have ice in the other one or just ice?
One of them is ice water and one of them is lukewarm water.
With ice in it?
No, lukewarm water. So like hot and cold. But I don't want you to burn yourself, so I'm saying lukewarm. Hot water, cold water. Now, put very cold water and relatively hot water without burning yourself. Next.
Wash your hands.
Put a room temperature bowl of water in the middle. Okay, so room temperature in the middle, hot on the left, cold on the right. Put your hands in the hot and cold bowls of water for at least 15 seconds. And put them both in the middle container of water and describe what you feel. And I want you to talk in the video. So if you're doing this, you're going to be recorded. So Luke might be doing this. Luke puts both his hands in the room temperature water, like normal water, okay? Whatever comes out of the faucet normally. And then you're going to describe what you feel in each hand. And it's kind of interesting. You'll see it. I don't want to give it away, okay? I don't want to give anything away, but do it. It actually is cool. Now, what that does is it really explains temperature as a relative term. Because when I say, a minute ago, what did you guys say? It's cold in here, right?
Yeah.
You're like, oh, it's cold in here, it's cold in here. Relative to your body temperature, it's cold. Agreed?
Yeah.
But when it's 100 degrees out in the summer, you would say it's hot, right? Even when it's 90 degrees out, with the humidity, it's still pretty hot because it almost feels like 100 here. But ever notice anything like less than 90 in the summertime? It's not bad. It feels pretty nice, right? Well, your body temperature is 98 degrees. So to you, it feels like a cool day because it's lower than that. So temperature is a relative term. Right now, the hot cocoa might be hot compared to your body, or the water is cold. They're relative terms compared to the environment around them. So hot doesn't mean anything. If I say that the temperature of that water is hot, that gives me nothing at all. It just says it's hotter than what I expect my body, or hotter relative to what I'm considering. So to quantify temperature, we came up with temperature scales. So hot and cold are relative terms. It's always compared to something else. So when you come in from jogging in the wintertime and it's freezing out, you come inside, what happens? You start to sweat and burn up. Because now your body's hot compared to the inside temperature there, right? You're starting to sweat. But when you're outside it was so cold that you didn't really notice it. It's a relative term. Okay, relative idea. Alright. Which we already talked about. But it's when two bodies in physical contact and have identical temperatures. Okay, so the room could be in thermal equilibrium. So for example, this desk, although it might feel colder than this piece of wood, they're at the same temperature. The room is in thermal equilibrium. We will talk about this in section 10.2 and 10.4 about why they feel different, even though they're at the same temperature. This feels really cold right now. It's at the same temperature as this, which does not feel cold at all. Does that make you wonder what the heck's going on?
They're just material.
It has to do with material properties, yeah. But we'll talk about why more in the next section. So, cold feels normal. They're at the same temperature. Okay, and I'm not going to discuss why just because I want to wait, but I'll definitely let you discuss why tomorrow. Okay? You take a can of soda. What's room temperature, by the way? Anybody know? About 70 degrees, yeah. Room temperature is about 70 degrees. These are numbers you should know. Okay? The freezing point of water, 32 Fahrenheit. The boiling point of water, 212 Fahrenheit. The freezing point in Celsius, which we'll talk about later, 0 Celsius. The boiling point, 100 Celsius. That scale makes much more sense, by the way. As always. Look, who would have thought metric makes more sense. Room temperature in Celsius, I think, is like 23 degrees Celsius. Anyway, so say you take a can of soda at 70 degrees Fahrenheit, okay, room temperature. You put it in a cooler of ice, which is clearly at like 22 degrees Celsius, something like that, right? Fahrenheit. So 22 degrees Fahrenheit of ice, 70 degrees Fahrenheit of soda. Put the can in. Where will the temperatures of both ice and the can be when they're at equilibrium? Be careful with your answer. So the ice bath in the cooler is 22 degrees Fahrenheit. Here's the ice. Oops. Dyslexia? No. What's that when you put the letters in the wrong order? Is it dyslexia? I thought it was what you saw backwards, dyslexia. I don't remember. And then the 70 degree Fahrenheit soda. Okay? So you put the soda in the cooler of ice. At what temperature will they both be at when you're in thermal equilibrium?
Doesn't it matter how big the jar?
Absolutely. So give me an idea of the temperature. You can give me a range of temperatures.
It's very close to the temperature. Probably like still be 22
Close to the 22 though, but not exactly. Why?
because it's still going to change.
Still gonna.
Like even if it's completely negligible.
Good help, Jim. Negligible, good. It'll gonna be what? Still gonna meet somewhere, right? So although the ice is 20 degrees, it's got to move up in temperature a little bit. A little bit, even if it's a tenth or a millionth of a degree. James.
Well, because all the extra energy from the soda is getting dumped into the ice.
That's exactly right. Energy transfers, and we're going to talk about heat transfer in the next section, from hot to cold always. So, remember, we said what is hot? Hot's a relative term. So the soda is hot compared to the ice. So all that extra energy in the soda is being transferred into the ice, causing the ice to melt a little bit, or its overall temperature to raise a tiny bit. So maybe they'll meet at 22.5, somewhere in between. So how do I write that? I write it like this. Not less than or equal to, but just less than. Okay? Somewhere between those temperatures, but definitely not at 70 or 22. Somewhere in between those temperatures, exclusive, not inclusive. So you see already, your inequalities, you're learning math, compound inequalities. It gives you a range of values here. Okay, very, very applicable. Did you raise your hand at all?
No.
Okay. I thought I saw you stir at some point. All right. Thermal expansion. From chemistry, what is thermal expansion? And you can read it, obviously, but give me your own words. We learned this in chem real quick.
Something gets warmer and expands.
Yeah, so, for example,
Water and ice.
water is an exception. This is a general idea. Water, there's an exception to it.
Thermometer.
Thermometer of mercury. Oh, who would have thought a thermometer? Look at that. So a thermometer is a fixed mass of mercury or whatever the solution is now, iodine, alcohol solution. Okay. Now, when you add heat to it, its volume increases, which causes it to rise. It's the same amount of mass. It's a fixed container. But look, the volume was 0.1 milliliters when it's at 0 Celsius. When it's at 50 Celsius, it's 0.101 milliliters. It's the additional 0.001 that is increased in volume. Thermal expansion says things increase as the temperature increases. James.
Well, like, when you hear weird noises in the house, it's usually either settling or expanding. At night, like the cooling that occurs causes the wood panels to actually constrict and make noises.
Yeah, there are a lot of really, really major applications of this. That's one of them. It's like a door also. In the summer, ever try to close a wooden door that doesn't close? The wood expands in the summer. Wood swells from humidity and temperature both. So in the summertime, it's so difficult to close some wooden doors. They'll like get caught. Or how about, you want to give me an example before I give it up?
Well, he said it happened in The Conjuring.
In what?
The Conjuring versus The Conjuring.
Oh, good movie. I saw it twice.
That was whack.
I haven't seen it.
Yeah.
Also,
As soon as the monster
Sadistic, is that what you said?
it just starts like throwing people, and just starts shifting over each other like, no, oh my God.
Focus, focus,
or
focus.
like with
That's the scariest movie I've seen.
That was
since
the
Sixth
big
Sense.
That was a whack movie.
Guys, stop. I don't care. No, I don't care, but stop. James, go.
Or like with dental implants, they have to try to match the implant's index of thermal expansion to be very close to that of an animal.
That's exactly right. Guys, think about it. If you eat something hot and you have a cavity filled, the material that they use I think it's a resin or an epoxy
Yeah,
actually,
it's a plastic resin.
plastic resin, it needs to have the same thermal expansion properties as enamel. Or else when it's hot, what's going to happen? It's going to expand and it's going to hurt your tooth. It might crack your tooth. So it's exactly the same. Now, they use an infrared gun. It's a little orange like shield it looks like, and they put it up to your tooth. And that actually causes the resin to solidify to the exact density and everything that you want it to be. And then there's a little beep, and it goes beep, and the guy knows it's ready. He might not know what's going on really, but I hope he does at least.
That's cool.
Oh yeah, gold
It's really
also has a very similar index.
Which makes sense as why it's
Because that's why they
gold fillings.
yeah.
Other examples. Which people don't always recognize other examples. One of them is tires in a car. In the wintertime, what happens? Tires shrink. They're a little deflated. You always need to add air to the tires in the wintertime because the pressure goes down and the volume goes down because the temperature goes down.
Water.
Also, yeah.
Water is like the opposite of this.
Water to ice is the one exception because of the hydrogen bond. The hydrogen bond, its angle becomes more obtuse when it becomes a solid, which is a decrease in temperature. So it is definitely an exception. Due to that, though, fish can exist. Without that, fish would not live. Think about it. Fish live under the frozen surface. Well, obviously in salt water, in freshwater fish. Freshwater fish would die if this were not true. Ice on a pond freezes on the top. The whole bottom is less dense, is more dense. So the water underneath is more dense because the ice expands. So the expansion of ice makes it less dense, which is why it floats in water. When you put ice in a cup of water, it floats, right? Just like the ice at the surface floats up to the top, that starts to freeze. As soon as things freeze, it moves up. The water below is actually liquid, so the fish are still living in fresh water. Another example, ever go on a bridge and you see in the bridge, there's little gaps with like metal teeth that are like notched? Think about like you're on a bridge and there was like a cut in the bridge and there's these little metal teeth and they lock in on both sides.
Oh yeah.
That's for allowing for expansion and contraction and temperature change.
Oh, that's cool.
On land, there's not much you can do about it, and the roadways are made of material that allows it to expand, but you still see in the wintertime lots of potholes.
Yeah.
Because suddenly everything starts to contract, and when the molecules were suddenly like nice and separate, and they're contracting, it's going to cause little breaks and tears. And then when cars roll over it, it breaks even more, it propagates. It's a change in temperature that causes potholes.
Would, like, I know it's like earth movement and stuff, but wouldn't like part of earthquakes be responsible? Like, wouldn't that have to do with that?
Earthquakes are tectonic plates
I know,
moving.
like I know that partially. Like,
I don't think so, but I mean, if you research it, maybe you can tell me more. But I've never heard of that. It's possible. Okay? All right. Let's go to the next slide. All right, common temperature scales. You guys should know these scales, Fahrenheit and Celsius, right? You've heard of them before? Okay, you have a general idea of them? Now, the 32, what is the 32?
Freezing point in ice.
Of ice in Fahrenheit, right? In Fahrenheit. So take a look. What's the freezing point in Celsius? Everybody should know this. 0. Plug in a 0 here, what do you get?
32.
So that's the freezing point in Fahrenheit when you plug in 0 for Celsius. So this 32 is indicative of the difference in the freezing point value of each scale. Okay? Both scales can have positive or negative values. That's all we're going to say for now, really. Okay, let's go to the R stands for Rankine. K stands for Kelvin. Rankine and Kelvin scales are called absolute because they cannot be negative. The lowest possible temperature in kelvins is 0 kelvins. By the way, you don't say degrees Kelvin. Write that note down, you'll see it here. I actually wrote it down later on. 0 degrees Rankine, you do say, or 0 kelvins. Kelvins are their own unit. I don't know why they do this, it's weird. But the metric system started with kelvins, not degrees Kelvin. And it's lowercase k when you're discussing the actual amount. It's capital K when you're naming the scale. Random, I read about it last night. Sorry. I was writing your notes, that's why I read about it. They all laughed at me.
Is the centigrade temperature that actually exists in the measurement system?
Did what?
Centigrade, is that actually?
Centigrade is Celsius. Same thing, yep.
Right.
So, let's discuss what this means. It's really kind of cool to think about absolute zero. Okay, when you get to absolute zero, all thermal motion does not exist at all. Molecules stop moving, bonds stop being like vibrating, there's no rotational inertia for anything, everything stops at 0 Kelvin or 0 Rankine. They're at the bottom of the scale. So 0 Kelvin is negative 273 Celsius. That's how far down it is. 0 Rankine is negative 460 Fahrenheit. Negative 460. Helium, liquid helium, liquid helium is around 1 Kelvin, I think it is. It's like the closest thing you can get down there. Now, why can you never get to absolute zero? You have to think about this one for a second. How come you can never get to absolute zero? It's really weird, but it makes so much sense if you think about it. We've never reached 0 Kelvin or 0 Rankine. It's impossible. We've gotten to 0.001 Kelvins, but never gotten to 0 Kelvin. Why is that?
Is it because the molecules and everything is always moving?
Theoretically, that could be an answer, but there's one that makes more sense than that. That makes sense. Obviously, something that has to always be moving. But there's one that makes it a little easier to understand.
The sun.
No? Good idea, though. Not the sun. Here, I'll give you a hint. Here's your hint. You want to guess first?
Does it have something to do with the four basic forces?
No. Maybe some other theory, but this is different. All right, here's your hint. How do you cool down something that's warm?
Wait, is it you can't totally stop the motion part?
Well, that's what she was saying, but that is part of it, but it's an easier
I see
explanation.
what it is. Since you don't have anything that is at absolute zero already with which to cool down things that are close to it, there's no lower you can reach.
How do you cool down a soda? You put it in a refrigerator, which is colder, right? So how could you cool something down to zero if there's nothing less than zero to cool it down with? What came first, kind of, you know what I mean? Like, you can't get there because there's nothing to cool it down with. There's no negative Kelvins or negative Rankines to cool something down with. So you can't get to zero because you've got nothing colder than zero. The only way you can ever get to 30 Fahrenheit is to cool it in something less than 30 Fahrenheit, right? Due to Q equals MC delta T. That's the reason. Due to heat transfer. It's because of heat transfer. To cool something down further, it needs to lose its heat and give it to something else, right? I can't give away my heat to something colder than me if I'm the coldest thing there is. Doesn't make sense. So there's no refrigerator that could be lower than zero to cool something down to zero. Put it that way. There's no refrigerator that could be colder than absolute zero to cool something down to absolute zero, since absolute zero is absolutely zero. There's nothing lower. Okay? Don't yell Tori in the assumption that you're going to chatter. She's going to check her chat and then laugh.
Is that what's going on?
Oh, I'm going to take a wild guess and say it is.
Well, you're wrong.
Anyway, take a look at this next slide. So we have an idea of some applications. You know these already? Okay? You know this as freezing point and boiling point. In thermodynamics, you call it the ice point and the steam point. Same words, okay? Same words, yeah. There's no Rankine on here. Rankine's not used as widely, but I thought you should know it. Come on.
Thing we did yesterday, and wait, no, I'm thinking English.
9-2, 9-3, 10-1, 10-2, 10-3 on your next test.
It's not on the formula sheet.
This is not on the formula sheet. Everything we did yesterday was. Everything through chapter 9 is on the formula sheet. I'm going to update it, don't worry. I'll put a new formula sheet on Moodle. And the laminated ones will be missing the temperature formulas. I'll just put them on the top of the test. Yeah, I thought about that last night. So right now I was writing my notes. So, the temperatures, because I keep saying it, it sounds so stupid. The temperatures here, okay, are temperatures you should really know. I'm not going to put these temperatures on the formula sheet. You really should know them though. Okay, although Kelvin 0 you could figure out. Okay, based on the formula. If we go back.
And you forget to save, and you're just like, oh my.
I know. All right, so we forgot to record. Just read this.